Hi, today we're going to look at surds and some of their properties. Before we do that and talk about what surd is, I want you to pause the video and think about what different types of number are there. What does that mean to you? Would you classify them into different groups? Have a think. Well, this is quite an open question. Often the responses are things like even and odd numbers, square numbers, maybe cube numbers, prime numbers, and that's all good. But sometimes we classify numbers according to other properties. And I think I'm just going to show the picture and then talk about it. So this is a Venn diagram of loads of types of numbers. Right in the middle are the counting numbers, also known as the natural numbers. 1, 2, 3, 4, 5, 6, 7, and so on. These are sort of probably the first numbers ever invented when people started counting. If you throw in negative numbers as well, including 0, actually 0 is not on here, but it wouldn't be interestingly, it's not considered a natural or counting number, but it is a whole number, so it's in there as well. And note that 1, 2, and 3 are also whole numbers because they're enclosed inside. And we use this sort of Z to show that. You might have seen that before, maybe not. I'll just draw it out as I would do it. So I would draw a Z and then just trying to draw a little bar like that. Sometimes it's called blackboard bold Z, I think. And these are all examples of rational numbers. Here's a key one. You will have seen this word before, I think. Oh, by the way, whole numbers are also called integers. Rational numbers can be written as a fraction. So things like a half, minus 2/3, 2.25 can as well, because you could write 2 1/4, which you could then write as 5, not 5/4. So 2 1/4, 9/4. Note that minus 1 is a rational number because you could write it as minus 1/1 and so on. You then get irrational numbers, and we can categorize these in a few different ways. There are some that are called, oh yeah, so it says irrational here. Don't get too hung up on this, but there's real algebraic. So that is numbers that are the solution to polynomial equations. So x squared equals 2 has the solution x equals root 2. X squared, or minus root 2 actually. X squared equals 3 has the solution x equals root 3 or minus root 3. And then you get things like this as well. And even things like x cubed equals 3. The cube root of 3 would also be a real algebraic number. And then there's other ones that are known as real numbers, but they're not algebraic. There's no way that you can solve a polynomial to obtain their solution. How do you know that? Well, that's not something I'm going to talk about today, but some special numbers. Pi, minus 2 pi, even 1 plus pi. Basically, most things involving pi. Root 2 plus pi. And another number called e, which we'll be talking about, but I'm not going to say any more on that right now. So those are some types of numbers. There are actually numbers outside of the real numbers called complex numbers, and even ones beyond that. So I'll just go and write that here. But I don't think I'm going to talk about that here because I don't want that to be the focus. You can look these up if you like. So the key thing, the next question, I just realised I've kind of got rid of it, but what is a surd? Now a surd is a special type of number, and it's basically going to be these ones here, but it's not going to include things like a half. So it's all of your roots and your square roots, things involving roots where you're adding cube roots and so on, but they don't simplify to nice numbers such as root 4, which simplifies to 2. That's not a surd because it would lie within the whole numbers bit, sort of a bit disguised. So basically it's this bit I'm shading in here, but not this bit here. That's going to be our surds. And I may have answered the next question for you already, but what things look a bit like a surd but are not? That's things like I said, root 4, basically the root of any square number, root 100, and also the cube root of cube numbers. So the cube root of 27 looks a bit like a surd, but actually it's 3. Sometimes things are a little bit more disguised, which we'll see later on actually. It can involve lots of roots, but potentially it could simplify to one of these numbers here. I'd say I'm pretty confident things like root 2 plus pi, that is actually not a surd because immediately you've got things like pi in there. So you'd be within the real numbers but not the real algebraic. Although having said that, a lot of what we're doing could still be applied, well, basically everything we're doing could still be applied to this kind of number. So it's not too much of a worry if you do classify that as a surd. Right. Now I'm going to ask you to have a go at a true or false sheet. Here it is on the screen. Write true or false next to each one, thinking about it carefully. Alright, here are the answers. This one is false. You can't, because you've got a root around here and a root around here, you can't just add the numbers and then put a root around it. You can see that's true because 3 plus 2 is equal to 5, which actually is the square root of 25. This next one is true. That's the definition of when you times a root by itself, you'll get the number inside the root. This one is also true because when you're adding, you can't do it, but when you're timesing, you can actually just you can put a root around it and put the two numbers inside. So the root of 9 times 4, which is root 36, which by the way is 6. As you can see, this would be 3 times 2, which is 6. So you can see that it works. But that will always work. Root 2 times root 2 is 2. We've sort of already established that. So it's 2 times root 2, which is 2 root 2. This one's true. The next one sometimes catches people out. Well, you learned earlier on in school that 4x plus 5x is 9x. So if we just let x equal root 3, we can see that this works. It's true. And just be careful here. We've got 2 times 4 is 8, but it's root 3 times root 3. So actually it would be 8 times 3. This one was false. The ones up here, never quite know what they're trying to get at with this question. I'm going with false for all of these, and the reason is that root 2 actually goes on forever. So it looks like they've rounded it. That's what I'm assuming. I think that's what it's trying to get out. This one is false for the same reasons that this one was false, number 1. And finally, this one is true. Just like, actually, you can even see that it's sort of just a rearrangement of this one over here. If we divide two surds, then you can basically then bring the root inside 36 over 4, which is root 9. So that's true or false with some numbers. How about some more general statements? Fill in equals or not equals. Pause video, try this out. So we're working generally here because actually in the case that a and b was 0, this one would be true, but in general for like most numbers, it's not equal. Make sure you're aware of this. We're going to have to find other methods for adding surds. Same goes for minusing. However, if you're multiplying, it's equal, and if you're dividing, they are equal. You can bring them out and have them separately or have them together. By the way, this would also be true for the cube root or the fourth root. We're just using the square root because that's generally what we look at in A level, and let's just focus on that. Here, well, the root of x squared is x, and the root of y is y. So actually, this one's going to be equal. But as soon as you put the root around the whole thing, it is not equal. And you could write some numbers down and see that that is the case. This one's true. It's going to be x times y. And this one is also true because you can put the root around x squared, the root around y squared. They're equals. So, but I'd say this is the one to be careful of. I see people make this mistake. Especially when dealing with circles later on. Things like x squared plus y squared equals 4. Sometimes people then write x plus y equals 2. They take the square root of everything. You can't do that. That doesn't work. That is what is, I'm saying here. Hopefully you're happy with that. It's a very quick recap of Surds. I'm kind of assuming you've seen Surds before. You might just have forgotten the definition, but otherwise you might need to go revise it a little bit, because these are the rules I'm assuming you know. We're now going to look at applying some of them in different situations. The rest of this lesson is basically going to be me reminding you about how to do certain things with Surds and then you having a go. Really important that you have a go, otherwise you're just watching me do loads and loads of examples. When we say simplify Surds, we generally mean write it, so maybe I just demonstrate it. So root 12, we can actually write as root 4 times 3. Okay, there's nothing wrong with that. 12 is 4 times 3. And then I can use one of my rules above to write it as root 4 root 3. Why would I want to do that? Because now I can write it as 2 root 3. And this is considered simplified. I've got something inside the root that doesn't have a nice factor that goes into it, like a square number, and something outside. No, I've gone with 4. I basically looked for a square number because that's why I didn't do 6 times 2 because 6 and 2, neither of them are square numbers. So square number here. All right, I want you to have a go at these 3 questions here. Pause the video. 72. Okay, it's going to be actually a good idea because sometimes you can't quite see what square numbers go into it. So maybe just write them down by the side. 1, 4, 9, 16, 25, 36. And my initial thought is that this was going to be 9 times 8. And I'll talk about that in a minute. But actually, 36 is a bigger square number. So you always want to go with the largest square number that goes into it. So it's going to be root 36 times 2, which is root 36 root 2, which is 6 root 2. You can, if you're feeling confident, just go straight from here to here. I'm just going to put this extra step in. Now, if you had written root 9 times root 8, which I'm just going to go straight to here, that's okay. We then get 3 root 8. It's just that we could then simplify root 8 further, because we could write it as 3 root 4 root 2. And root 4 is 2, so it's 3 times 2, which is 6, and we get to the same answer, just a longer method. So it's worth having that, just thinking about that. Always look for the largest square number. Okay, I didn't spot it straight away, so I wrote them down. 150. Okay, it's got a 0 on the end, so 25 is going to go into it. How many times does 25 go into it? It's going to be 6 times, isn't it? So it's going to be 25 times 6. By the way, I didn't say this, but you should be doing this without a calculator. Yes, A-level maths can involve a calculator, but these are all like crucial skills. You can get asked questions with algebra in as well, and it just falls apart. So try and make sure you're confident with this without a calculator, otherwise you will run into problems later on. This becomes root 25 root 6, which is 5 root 6, and I can't do anything more with that. Finally, a bit of a cheeky one here with the cube roots. It's going to work in a similar way, but now instead of finding the largest square number, we're going to find the largest cube number that goes into it. So that's actually 27. So it's going to be the cube root of 27 times 3, and we can still use the rule of Surds. So the cube root of 27 times the cube root of 3. And actually, the cube root of 27 is just 3. So it's 3 times the cube root of 3. Just make sure you draw that little 3 really small there. Hopefully you're happy with that. I'd say, just as an addition, like, don't get too stressed about this one. Generally in A-level, we're looking at ones involving square roots. Right, what about some simplifying? So we're adding some surds together or subtracting them. Well, I'm going to go through one as an example. I can actually get rid of these brackets. They sometimes make things a bit more complicated. The reason I can get rid of it is that we're adding the surd. So it becomes plus root 3 and then minus 2 root 2. Now what we can do is we can actually add the whole numbers together, or the rational numbers as such. So 5. And then the root 2 minus 2 root 2 is going to become minus root 2. It's as if it's saying x minus 2x, which is minus x. The same idea. Right, have a go at these three here. So in this next one, it's going to be 4 minus root 3. Just need to be careful now. We're minusing, and what we do is we minus 1, but then we need to deal with the fact there's a double negative, so it's plus 2 root 2. And then it's minus 3 root 3. And what do we do with that? Well, same again, really. Combine the rational numbers. So we're going to have 3. Then it's minus root 3. Actually, let's put the 2 root 2. There's nothing I can do. I can't combine that with the root 3. They're different surds. And they don't, they can't be sort of turned into one another. So I'm left with minus root 3 minus 3 root 3. That's going to become minus 4 root 3. Slightly trickier ones now. How do we subtract surds like this? Do we leave it like we did with the root 2 and the root 3? Is that the answer? Or can we do a bit more? Well, the answer is we can do a little bit more, because even though we can't do this, we can, if you remember, do this. If we can make it so you got the same surd here and here, then we can add them, just actually like we did in the last example. So the thing to do is to try and simplify each one individually. And I'm going to do this a little bit quicker now, but we can write 32 as 16 times 2. So it's root 16 root 2. That works well because root 18 is root 9 times root 2. So that becomes 4 root 2 minus 3 root 2. And suddenly we've made them actually quite nice. They're just involving root 2, and the answer is root 2 by itself. I bet you didn't think that was going to be the answer. Root 32 times root 18 is root 2. And if you weren't sure about that, but you understand it now, try this next one. Well, 11 goes into all of these, and actually a square number can be multiplied by it, so it's going to be root 9 root 11 plus root 4 root 11 plus root 11, which gives me 3 root 11 plus 2 root 11 plus root 11, which is 6 root 11. Of course, I could, if I wanted to, write it back as a single surd. It's worth talking about this. It would be root 36 times root 11. And that's going to be 36 times 10 is 360. If I then add on 36, I think I'm going to get 396. So we can add surds and leave them as like non-simplified surds. Easiest to leave it like that, but be aware you could convert it back inside the root as well. Alright, what about when we're multiplying surds? Well, we did see above with the rules. I haven't talked loads about these or where they've come from. I'm not going to do that right now. It's best to look at it when you're dealing with indices, because you can actually use indices to write each of these. But I can bring it inside in this case. So actually there's two ways to do this one. First way is to just bring it inside. 2 times 6, which is root 12. This is not yet simplified because there's a common factor of 4 and 3. I'm going straight to that. This is 2 root 3. The other way you could have done this question is actually you could have written it as root 2 times root 2 times root 3. I've actually separated the root 6 into root 2 times root 3, and then recognize that this is 2, which would again give me 2 root 3. So you can decide which method you use in this sort of question. Maybe safest to use the top one, but probably quickest to use the bottom one. Do be aware of it, because if I don't know, there's just questions that come up sometimes that it actually helps to do this sort of thing. Okay, try these three. So if I use the quick maths method, we could write this as root 5 times root 2 root 5. That's what root 10 is. I've kind of recognized to try and get the root 5. And then root 5 times root 5 is 5, so it's going to be 5 root 2. You could have gone for root 50 and then got it by simplifying the surd. And why is this method good? Because I don't really want to be doing 8 times 7 times 6. It's not going to take that long. But check out what I can do. I can actually write it. I think it's best to, let's simplify the root 8 straight away. So it's going to be root 4 root 2. That's the square number that goes into it. Then I've got root 7. Then I've got, I could write root 6 as root 2 times root 3. And this is really good. So I hope that makes sense. This is the root 8, this is the root 7, this is the root 6. Well, the root 4 gives me 2. But the root 2 times root 2 also gives me 2. And I'm left with 2 times 2 times root 7 times root 3, which I could just write as 4 root 21. Best to just get it as a single surd at the end. And this last one, it really helps again to do this sort of thing. Let's just, we can see that there's some common factors, like there's a common factor of 2 going on and a common factor of 3, and actually a 5 as well. So this is going to work out really nicely. 2 root 3 root 5 times root 2 root 3 times 3 root 2 root 5. Well, I'm going to get root 2 times root 2, so that's going to give me 2. I've already got a 2 in there. I've now got a root 3 and a root 3 and a 3 in there, so it's going to be 3 and a 3. And then finally I've got a root 5 times a root 5, so I'm going to get a 5 coming out. So that's going to give me 4 times, actually what's the best way of doing this? Probably best to do 2 times 5 is 10. 10 times 9 is 90. It's going to be 180, which you might not have expected to start with. So be aware of that. If you did 15 times 6 times 10 and then simplify the surd, that's going to take a lot longer. This is a much quicker method. And finally, just want to remind you about multiplying out surds. So to do this, it's like the, I call it the crab claw method. So actually, let's do it in red. I'm going to times the, oops, we're going to times the first two terms. So that's going to be 2. And then the first and the last, that's going to be minus 4 root 3. Be aware of that. And then this one and this one, which is going to be plus root 3. And this one and this one, which is going to be minus 2 root 3 times root 3. Notice I went straight for writing the nice whole number first, and then I put the surds after it. That's good practice. Otherwise, you'd have to put a time sign in. It just gets a bit messier. So I'm going straight to that. Okay, and then you get a little crab. Hopefully you're happy with expanding double brackets. If not, practice that. So where does that leave us? That leaves us with 2 minus 3 root 3. And then this is minus 2 times 3, so minus 6. So I think it's going to be minus 4 minus 3 root 3. It's going to be negative. that makes sense because this one here on the left is positive, but 1 minus 2 root 3 is definitely going to be negative. Get quite a large negative number coming out. It goes then, can you try these ones here? Right, let me talk through them. So here we get root 5 times root 5. I'm going to straight away write that as 5 actually. Then we get plus 2 root 5 minus 2 root 5. So you might have spotted that actually. Whenever you get something like this, like a minus b and a plus b, they cancel out. This is just going to cancel out. Minus 4, and we actually just get 1 as the answer. Don't be fooled by this question here. It's actually a double bracket. Sometimes I see people just wanting to square the 3 and square the root 2, but there's more going on. It's this here. So yes, we are going to square the 3, and we're going to get 9, but we also need to then minus 3 root 2. And then we need to do this bottom one here. I'm running out of split space, but you can see it. I'm going to be minusing 3 root 2 again, because it's minus root 2 times 3. And then I'm going to be doing minus root 2 times minus root 2. That's actually going to give me plus 2. So I'm left with 11 minus 6 root 2. And finally, this last one, you might be thinking, oh, why did you put this in? It's not quite as bad as it first looks, because you can decide which order you multiply in. And so I'm going to change it to root 6 plus 2 times root 6 minus 2 to start with, and then we got this after. Now why have I done that? Because I'm using my knowledge of this one up here. They cancelled out, so I get my root 6 times root 6, which is 6. Then I get a minus 2 root 6, but I get a positive 2 root 6. So they just go, and I've got minus 4. And suddenly this is looking a lot nicer because I actually have a rational number there. And then I've still got my root 3 plus 4. So it's just 2 times root 3 plus 4. Could even argue that's a nice way of leaving the answer. I'm going to multiply out 2 root 3 plus 8. Now all of this done without a calculator. So you might think sometimes you need a calculator, but think carefully about how you can order it. That is a reintroduction, let's say, of Surds practice, and it will come together. Just make sure you're being careful along the way and you're using all the stuff you've learned from algebra, expanding double brackets, maybe triple brackets if it was not quite so nice. Simplifying is the absolutely crucial thing, and then adding them. Just remembering the rules, that's the last thing to say. When what's not equal to, okay, really important to never just add surds like this, and what rules you can use. Well done.